Hey everybody, we're going to cover lesson 7.2 now. This is an extension of the discussion that was begun in 7.1 for the chi-square distribution on tests that we now call goodness of fit tests. The goodness of fit tests are just like what we did in 7.1, where we have a bunch of, we have a categorical variable with multiple categories. And we make a hypothesis about the proportions for each category. It's not, but the only difference between 7.1 and 7.2 is that we're going to start doing more than two categories for the variable. So let's go ahead and jump right in here. Goodness of fit. In our last lesson, we learned about the chi-square distribution and its relationship to the standard normal distribution. We saw that both can be used equivalently to test claims about a population proportion in binomial experiments with two categorical outcomes per observation. Now we outline the process for chi-square tests in multinomial experiments with more than two outcomes. These tests are often referred to as goodness of fit tests. We're just trying to decide how well the observed frequencies line up with the expected frequencies, how well they fit those expected frequencies based on some null hypothesis. Let's begin with that. Step 1, determine the hypotheses. The goodness of fit test makes claim about the proportions or probabilities for each outcome of a multinomial experiment. If there are k outcomes per trial, then the null hypothesis would be a statement about k proportions. Okay, there are k outcomes, so you need a proportion for each one. Because the sum of all probabilities in a distribution is always 1, the hypothetical proportions must add up to 1. For the null hypothesis to not be true, one or more of the proportions would be incorrect. Thus, the alternative hypothesis takes the form HA, at least one of these proportions is incorrect. I think I'm starting to use the phrase, not all proportions are correct. I don't like focusing on the at least one, it's a little confusing. Okay, so we'll do an example in a minute, but we're going to go through the steps real quick. So the second step is always collecting data. Using a sample of independent trials, each having k outcomes, the multinomial experiment is conducted by collecting categorical data from a random sample. For each outcome, the observed frequency O is the number of successes. The sum of the k observed frequencies is always the sample size. N is the sum of the O's, so the last observed frequency is not random. They have to add up to a specific amount, so the last frequency is the value that makes that happen. There are therefore k-1 degrees of freedom among the observed frequencies. Next, we compute the expected frequencies E for each outcome. As with the binomial experiment, the expected number of successes is always NP, where N is the number of trials, and P is the hypothetical proportion for the corresponding outcome in the null hypothesis. So you're just going to do an NP for each one of these P numbers in the null hypothesis. Those will all have to be a certain size. For approximate normality in a binomial experiment, we require the expected number of successes and failures to be at least 10. In the multinomial experiment, we soften this because with potentially many categories to fill, it can require unreasonably large sample sizes. So, we assume that the test statistic is approximately distributed according to the chi-square distribution if each expected frequency E is at least 5. And remember, the chi-square distribution is sort of an extension of the normal distribution. So those rules for approximate normality sort of find their way here. Step 3, assess the evidence. For goodness of fit tests, the test statistic is this chi-square statistic, which we've computed. The distributions of values for the statistic have various shapes depending on the degrees of freedom. In all cases, however, the distribution starts at 0 and is skewed to the right. So you have all these different distribution shapes with degrees of freedom. To compute the test statistic, we need to know the observed and expected frequencies, and that's for every outcome. The null hypothesis gives probabilities for each outcome, and from these we can compute the expected frequencies. Again, each expected frequency is n times p. If the null hypothesis is false, the test statistic should be large because the observed frequencies will be quite different from the expected frequencies, e. So the differences O minus e will be large. This is why a goodness of fit test is always right-tailed. When the null hypothesis is false, the test statistic should be large, whatever that means. The p-value is determined using technology. It's the area of the right tail starting at the test statistic under the chi-square distribution with k minus 1 degrees of freedom. Okay, so we'll make this computation for the test statistic, find the area of the tail using a Desmos document for chi-square p-values. Step 4, you make a conclusion. So when the null hypothesis is true, the p-value is the probability of obtaining a test statistic that's at least as extreme as the one observed. Small p-values, less than or equal to alpha, provide sufficient justification for the rejection of the null hypothesis in favor of the alternative. Large p-values do not justify the rejection of the null hypothesis. So that's the same old rule as always. Try these. In the article, Is There a Season for Homicide? The author gave seasons in which 1,361 randomly selected homicides were committed. These values are summarized in the table below. So again, you have 1,361 murders. They're broken down into the 4 seasons, just depending on when they were committed. Keep in mind the total is given up here. It's 1,361. This is the sum of the observed frequencies, which you may remember is our sample size. Now remember the level of significance here. We're testing the claim at a 0.05 significance that the proportions of homicides for the 4 seasons are all equal to 25% against the alternative that they're not all equal. Okay, so they gave us a null and alternative hypotheses. Now, think about the first question as we go through this. Step 1, determine the hypotheses. Question 1, the outcome for each trial, which is a murder above, is the season in which the murder was committed. How many possible outcomes are there per trial? You're just saying how many categories are there here. So I'm hoping you said 4 categories or 4 outcomes for each murder. Okay, and then what are the hypothetical proportions? Well, the claim is that they're all 25%, so we would say each one of these would be 0.25, like that. For each season, so 25% for winter, 25% for spring, 25% for summer, and 25% for fall, just like that, easy as it gets. Okay? Now, what's the alternative hypothesis? We would just say that these are not all correct. So the proportions, I'll say HA here, the proportions, are not all correct. Okay. Could be just 1 or 2 are wrong, and the other 2 are right. So we just don't know which ones are wrong. Okay. And then step 2, we collect the data. So we've already done the sample size, which was the sum of the observed frequencies. This was the 1,361 here that was given to us. So we can put that in here. Okay. Now just remember the expected frequencies are all n times p. Okay, so n was 1,361. And then the P's are the proportions, and of course they can vary, but right now they're set as 25% for each season. So we'll just multiply each of the 1361 by 0.25. Okay, take a second and do that. And I would encourage you to pause if you need time. You want to fill out this table. Alright, so these all come out to be 340.25. Okay, and it's the same for each of these because they all have a 25% hypothetical proportion. Just like that. Okay, any questions? Let me know during the office hour or your break. Okay, so then do the expected frequencies satisfy the conditions? Just as a reminder, the expected frequencies are all at least 5. So yes, each expected frequency is at least 5. Okay, so that's all that's required. Degrees of freedom for the test are the number of categories minus 1. As a reminder, there were 4 categories. That's different from the sample size. The sample size is 1361, but all of those outcomes fall into one of 4 categories. So 4 categories minus 1, that's 3 degrees of freedom. Okay, just remembering again that we know that the sample is chosen up front. So you're starting with 1361 as your sample size, and the first 3 values get to be random, but the last one's going to be a number that makes the total 1361. So that's not really a random value. There's only 3 degrees of randomness or degrees of freedom here. Okay, any questions? Let me know. And now we have to kind of pound out another part where we start working on the chi-square statistic. So the chi-square statistic, you have to do O minus E squared divided by E for each category and then add that up. Okay, so I'm going to paste all the expected frequencies down from up here. Okay, now let's do the first one of these together. So as mentioned, you have to do O minus E squared over E, and this is going to be different for every row in the table. So the first O is 328 minus the E, which is 340.25. You see I'm trying to make a little space for myself. Okay, that'll be squared, and then again you divide by the 340.25. Okay, and that's all you're doing here. I'm going to give you a second. You can pause and work that computation out. Okay, so this should have come out to be I'm going to round to 4 places, so it should come out to be about 0.4410. And now I'd encourage you to try and do the rest of these. And then when they're done, add them up to get the total of all of those values. Just pause the recording now. Okay, so I'm going to continue by putting the rest of these values in. The next one's 0.1148. The next one is 2.9627. The next one is 0.5160. Okay, and if you haven't done the total, you can pause and do that real quick. Okay, the total should be 4.0345, like that. And that's our chi-square statistic. This value is the sum of O minus E squared divided by E. And again, that's called the chi-square statistic. So, like that. Same amount of variability in that as the sum of 3 z-scores randomly selected, squared, then added up. Okay. There's 4 values, but they vary like 3 squared z-scores added together. Alright, so our chi-square statistics 4.0345, we'll put that on the next page. Okay, and they're asking us to plot that down here on the graph. So 4.03 is going to be real close to 4. So I'll just kind of do that. Maybe I'll make a note down here, 4.0345 there. P-value will be the area to the right of this. Okay. Looks pretty big to me. Remember, the total area is 1 under any probability curve, and this seems like a pretty big chunk of that. Now, it's right-tailed tests. We're finding the area to the right. These are always right-tailed tests. Okay. Now, to get the p-value, we'll use the p-val calculator on the Canvas homepage for our course. Okay, so remember it's 3 degrees of freedom on this. So we've already done that. And let me pop over to Canvas again. We're going to have to put in that 4.0345. So here's Canvas. No, sorry, this is Desmos. It's going to have a different degree of freedom, so I'm going to change that to 3. Okay, and you should get, when you put that in, you should get a picture like this. But again, the chi-square value is different this time, so I'm going to delete what's there and put the 4.0345. Like that. And so now your picture that we drew should sort of match this. And you can see the p-value is like 0.2577 there. Maybe we'll say 0.258. That's really big. Okay. 0.258 is what we got. Okay. So that's really big. It's about 25%. So the p-value is 0.258. I think our alpha was 0.05. I remember kind of reminding myself right here, alpha is 0.05 on the beginning of this problem. Okay, so this thing is bigger than 0.05. Just again looking at the first 2 digits, 0.25 is bigger than 0.05. That's our alpha. So if it's bigger, we fail to reject the null hypothesis. Oops. And that means we can't support the alternative that those proportions are not all 25%. We write a brief conclusion. So the data don't support basically that the murder rates are not all the same for every season. I'm going to say murders are committed in different proportions by season. I don't know if that makes sense, but just each season has the same number of murders, or the same proportion of murders, I guess is what I mean to say. Okay? And that is it for that lesson. It's kind of short but sweet. See what you can do with it. Good luck.